Now, one situation that is often encountered in problems involving dependent random variables is that we know the marginal distributions of the random variables. We know the covariance structure between them, or the correlation coefficients between them, but we do not have any further information about their dependence. Obviously, this would be enough if those random variables were jointly normal, but they are often not. So how do we use this partial information to generate dependent samples? And for that, we actually go back to generating correlated normals. Let's state the problem in terms of two random variables, x and y. So we know their marginal CDFs, fx and fy, but what we don't know is the joint CDF or the conditional CDF equivalently, x given y or y given x. So we can't use what we did before in the that wave height and wave period example, for example, that we did. But what we know is we know the correlation coefficient between x and y. So we have this bit of information about their dependence. So the steps are we generate u1 and u2, two dependent standard normals, zero mean, unit variance, but a correlation coefficient rho prime between them. And there's a reason that we have rho prime here instead of rho, which is the correlation coefficient between x and y, and we'll come to that reason in a minute. So once we have u1 and u2, we obtain x from u1 through the normal CDF transformation, and y from u2. Let's take a minute to understand this transformation. What we do is that we equate the two CDFs, fx and phi of u1, phi being the standard normal CDF, and then we invert that relationship. So this way, what we have done is we have generated x and y true to their marginal distributions, and we have introduced some dependence among them because u1 and u2 are correlated. This can be generalized to n dimensions. We would simulate the n-dimensional standard normal with zero mean and the correlation matrix R prime, and invert that pointwise to obtain the x vector. Now, the reason is this nonlinear transformation between u and x, as we have alluded to before, does not preserve the correlation coefficient. So the row that we start off between x and y, and the row dash that we have between u1 and u2, they are not necessarily the same. In fact, if you want a certain row between x and y, you have to start with a desired row prime between u1 and u2. And there's a very nice paper by Professor Dirk Urigen, came out in engineering mechanics. You could read that for further information. Let's solve one problem involving such a transformation to show what's happening and all the steps involved. So we have seen this problem before. X and y are joint standard normals, and we exponentiate them to get two dependent Lognormals. We do not have the entire joint distribution of a and b, but we know the correlation between x and y. So what do we have in terms of the correlation between a and b? In fact, if we wanted a certain correlation between a and b, what is the correlation rho between x and y that we would start with. We know we have already determined this a few lectures back, what the correlation between A and B is in terms of that between X and Y, but here we are going to solve that by simulation. So we will find rho of AB by Monte Carlo trials. Here is the code. So we would define the random variable parameters in the beginning. X is standard normal, so is Y, and X and Y are correlated. So we define the correlation matrix, and we take the Cholesky factor of that, and then we generate two independent random normals, rand n, z1 and z2, and then combine them linearly to get the dependent y1 and y2 random variables. Y1 and y2 are normal random variables, and then we exponentiate y1 to get a and exponentiate y2 to get b, and we do this repeatedly, and in the end we can find the correlation coefficient between A and B. And here is the result of 10,000 such simulations at a range of values of rho. So you see the nonlinear relationship. The red line is the true known theoretical relationship which we have on the top, and the blue dots are the simulation results. So for example, if we want to have, or we know the correlation coefficient between A and B is 0.5, then we would have to start with correlation coefficient of about 0.63 between X and